Welcome everybody to the technical session 8 of SIBGRAPI 2021. This is a session dedicated to works that deal with remote sensing data. Well, my name is Gilson Costa from the State University of Rio de Janeiro, and I'll be the chair of this session. I'm also the guest editor of the special stream of the IEEE Geoscience and Remote Sensing Letters, in which some of the works submitted to the Geoscience and Remote Sensing Letters track of this edition of the conference have been published or are about to be published. In fact, the 3 last works that will be presented here have been accepted for publication in that special stream. Okay. So we'll have 5 short presentations of about 5 minutes each. And after each presentation, we'll have approximately 6 minutes for questions and answers about the work. Okay, the questions should be submitted through the YouTube chat and also on the session's Discord channel as soon as possible, because there's not too much time for the Q&A. Okay, so we may start with the first work called Seismic, Spatial Context Data Augmentation for Remote Sensing and Semantic Segmentation. This work the authors were Mateus Barros Pereira and Jefferson Alex dos Santos from the Federal University of Minas Gerais. So, we can start with the first video.
Hi, I'm Mateus from FMG, and today I'll present you the paper Seismic Spatial Context Data Augmentation for Remote Sensing Semantic Segmentation. Semantic segmentation is the task that aims at perform dense image labeling, and in remote sensing there are many applications that take advantage of this, such as urban monitoring, agriculture and environmental management, and many others. The problem is that it's too difficult to obtain images for remote sensing, and the label annotation process is costly for semantic segmentation because we are usually dealing with high spatial resolution images and sometimes we require specialists to perform the annotation. Because of that, we usually need to recur to data augmentation, that are methods that increase the training sample size and diversity. In this context, we propose a novel data augmentation method for remote sensing semantic segmentation called Seismic. Here's an example of a synthetic image created with Seismic. Here on the left side we have a synthetic image that is created with transformed patches across all the data set that are placed in this chessboard-like pattern, where the black spaces are meant to avoid spatial discontinuity. In the ground truth, the black spaces will actually tell the network that it should not backpropagate the loss for these spaces right here, so it doesn't learn these spatial discontinuity problems. And the final input, we take each one of these patches, mirror them to the following black space in order to avoid black squares being sent to the network during the forward stage. As the results will show, Seismic is especially effective under the condition of low amount of training data. It is easy to employ and one of the first, if not the first, work that studied the use of content mix techniques for semantic segmentation in remote sensing scenarios. So, how do we create images with Seismic? The first step is to divide the data in mini patches and pre-calculate their weights. This weight will tell the method how probable each patch is of being chosen to compose a new synthetic image. And this weight is proportional to the amount of pixels from the less common classes of our problem. So after pre-calculating these weights for all the mini patches, we will then randomly select the mini patches that will take part in the new image. We transform them and place them in the valid grid position of the new synthetic image being created, following that chessboard-like pattern that I showed before. Finally then, we mirror these images in order to avoid problems with black features being sent to the network. In order to test our method, we selected as the semantic segmentation network the pre-trained FCN ResNav 50, and we evaluated on 3 datasets: Coffee dataset, Vine dataset, and TET4 dataset. For the transformations to the mini patches, we chose to use vertical flips, horizontal flips, random rotations, transpose, grid distortion, and perspective transformation. As baseline to our method, we select the data warp augmentation, which is the most common data augmentation technique applied to remote sensing semantic segmentation. The transformations are the same that we used in the Seismic approach that I showed before, so it's a fair comparison between the two of them. Here are the results for each one of the datasets. First of all, for the coffee dataset, the results were pretty much the same, but that mostly because this is a dataset that only contains 2 classes and a lot of inter-class variance, so it's difficult even using complex data augmentation techniques. But for the urban datasets, we managed to get a better result in terms of normalized accuracy and intersection over union with Seismic, especially for the TET4 dataset. Looking at individual results for each class, for the Vine dataset, we managed to improve the car class from 74 accuracy to 76 using Seismic. This may not look too much, but considering this is a really difficult class to segment, this is an important result that we managed to achieve with Seismic. But for the TET4 dataset, we actually managed to increase the results for a lot of classes in a considerable amount. For example, vegetation went from 62 to 89% and bare soil from 75 to almost 100% with Seismic. The only class that we lost here was for the road class, but considering the improvement in the other ones, this is a fair trade-off. So in conclusion, Seismic is a novel data augmentation strategy for remote sensing semantic segmentation, and it's a promising method that showed that can improve the performance when compared to the use of data warping techniques, and it's especially effective for few labeled data. Thank you very much.
Thank you very much, Mateus. Very nice presentation, very quick, but very informative. Okay, so we have some time for questions. Well, let me start with this first one from Google. Was there any inspiration in self-supervised jigsaw patterns for the construction of these data augmentation techniques?
Yeah, it's kind of similar, but we use it for a different purpose. In case of the jigsaw patterns, they may look like this Seismic, chessboard-like approach. However, first of all, we are using this chessboard-like pattern because it is easier to construct synthetic image this way. We don't need to use GANs or any other difficult or computational heavy process. And we train like normally, like in a semantic segmentation network. We are not trying to reconstruct the image, to put the pieces in the right place, like in the jigsaw patterns from the self-supervised approach. So there's this kind of similarity, but in the end, they serve for different reasons.
Okay, I have a question. Do you just a second, Hugo? I will make your read your questions in a second. But you use this procedure for balancing classes in some way, like the underrepresented classes are kind of balanced using your method, from what I understand. Yeah. And then, do you still use loss function, weighted loss function later on, well, for training the method with this data augmentation procedure, or you don't weight the classes in the loss function?
You can use these weights, and if you use them, you can maybe improve the results even more. Just like you can also use a different loss function that works better with unbalanced data sets. In the case of the paper, we wanted to test only the Seismic method. We wanted to focus especially in that spatial properties of the data augmentation method. So we did not employ these different techniques, but it's totally possible, and and it's better to use them in practice.
Okay.
Because
But then the results that you've shown, you did not use weighted the classes in the loss function.
yeah, exactly.
You didn't.
Because we wanted to see only the performance of
Okay.
the mat compared to the baseline. No, nothing else to maybe bias the results or something like that.
Okay, nice. Okay, so we can go back to Hugo's questions. Okay, do you think other SSL augmentations like rotations or colorizations could also be used in the context of your work for augmentation? Can you combine it all? I mean, did you combine the various data augmentation possibilities at any point?
And in this work, we use that list of transformations that I showed on the presentation. We can employ different transformations as well. I mean, the Seismic method is I mean, you can use any kind of transformation you want in the mini patch. So depending on the problem data set, you may choose something different. Like, for example, the colorization, I did not use it because I didn't want to get much different from the normal images from the data set. And you can also combine the ESSL with this as well. You can, for example, pre-train the pretext task from self-supervised learning using any kind of method you want. And then when you're going to train the segmentation network, you can employ the Seismic images to get even better results. So they are not like, you can use both of them together and results probably will be even better.
Okay. All right. So let's see. Are there any more questions? No? Okay, so maybe we can go for the next work. Thank you very much, Mateus. So now, the next work, simplifying horizon picking using single class semantic segmentation networks. Well, there are a number of authors here from the IBM Research Center, Federal University of ABC, and well, that's it. So let's see the video then.
Hi everyone, my name is Danilo Calles and I'll be presenting the work Simplify Horizon Picking using Single-Class Semantic Segmentation Networks, made by me, Andrea Brito, Dario Augusto, Felipe Kawashita, and Maisa Macedo. Seismic data can be represented using a set of images that compose a 3D volume, called cube. In this representation, the interface that divides two different regions are called horizons, and the tasks of labeling it is called horizon picking. Horizon picking tasks is an important task in geological exploration and consists in selecting important regions over seismic images, like shown in those pictures. The process can be done automatically or manually. A common problem in horizon picking is to get the labeling data, and one can use automatic detection tools in order to label it. But even using those automatic tools, this process can fail at some regions, maybe the regions that are harder to identify than others, and the annotation must be made manually. In order to reduce this problem, our study proposed to reduce the annotation work by using a single-class approach with semantic segmentation neural networks and using the mesh optimization method to remove the noisy data. Mesh optimization is a post-processing method created in a previous work. We chose to use two state-of-the-art semantic segmentation architectures in order to accomplish this. The first is DeepLab v3+, and the second PSPNet, being both convolutional neural networks. For the train set, we use the Netherlands dataset, a public dataset created by researchers of IBM Research that represents 7 different horizons, with square images of 256 by 256 pixels. Here we show our method in this pipeline. The single class approach, or the binary class, tries to reduce the annotation work, while the multi-class is used as a baseline for comparing the results. The dataset containing the images and the annotation of it are used to train and test the selected networks, and each one of the predicted images are the input to our contour detection method, responsible for getting the horizons at each prediction. The contour obtained in the previous steps is used in mesh optimization method, resulting in a cloud of points with clearer data and less noises. Here we show some results of our work by comparing the mean distance between the ground truth and the predicted results, in which lower results are better. Our method achieved better results than the previous one using PSPNet. We've also compared the percentual area coverage with less than 80 milliseconds of distance, in which higher results are better. In this case, our method also achieved better results than the previous one using PSPNet. So, in general, PSPNet had better results than DeepLab v3+. This is mainly because DeepLab is a more complex network than PSPNet and it's harder to parameterize. Multi-class classification achieved better results than single-class classification, although we must consider the trade-off in this case. Single-class presented closer results and it was less computationally intense than multi-class. Considering both experiments with PSPNet, all of the horizons achieved better results if compared to the previous work. So, finally we concluded that PSPNet performed better than DeepLab v3+. We also concluded that our proposed approach allows less work on annotation process if compared to the multi-class approach, and also has competitive results. And for future work, we intend to improve the method to lead to better results with salt domes. Thank you.
Oh, thank you very much, Danilo.
Thank you.
Isa, thank you too. So let's see if we have questions. Okay, well, we don't have questions yet. So Danilo, can you tell me the importance of this work in the oil business? I mean, how important it is, and how hard it is to produce. You motivated the work saying that it's difficult to annotate, but tell me a little bit about this annotation process. What's in there? I mean, how long does it take? How hard it is?
Yeah, this annotation process made by geologists usually it is a hard process, and usually they use some automatic tools in order to label this data and get the desired layer that he wants to analyze. And then it's usual also to use some methods using like multi-class approach, which is computationally intense. So I think the main benefit of using our method is to use single class approach, which cost less than multi-class approach, and as we saw in those results, it can have it can have a result similar to this multi-class approach.
Mm-hmm. So in the single class approach, you use the class and no class. All the other classes are negative classes. Is that it?
Yeah, mainly we choose to use like one is for our class we desire to search for, and zero is considered background or other classes.
Or other
Which
classes?
in multi-class approach, usually zero is the background, one is the 1 to 7 is the desired class.
Yeah, it was not clear. Unfortunately, I didn't read the paper, but it's not clear for me how you combine the single classifications into a multiple classification to compare it with the ground truth.
Yeah, they are both separate. The multi-class is just a way for us. It's a baseline for our work. And the single class approach, it was 7 different models, just 7 trained models, which each one of them is responsible for predicting one of the classes.
So you got the higher probability of these four these 7 predictions, and assign it and use it to label the results, right?
You mean the single class use them to, yes.
Yeah, okay. So you got the higher probability for each single class map, mixed it together, and got the well,
Houston.
infer the most likely class. So yeah, Maisa.
For example, we have 7 different layers to predict, and we predict each one separately, and then at the final, we put all predictions together in a cloud of points.
Okay.
At the final, we have all points related to each class. Talking about your first question, how this is important to the area of oil and gas. Nowadays, geologists is a horizon picking because they pick each one of the pixels related to the layer that we would like to understand which kind of material they have in this layer. So they can use some, how can I say, automatic methods to help in this segmentation. But this kind of automatic segmentation of the whole layer can be very useful as the procedures involving ground is very expensive.
Mm-hmm. Yeah, I know that. People usually don't talk about numbers, but I know that the numbers are the money involved is astronomical. I mean, the amounts involved are really high. So any improvement in these techniques, in related techniques, are very important money wise. Okay. So, okay, we have a question here from Professor Jefferson. Thanks, Danilo and Maisa. 2 questions. Did you apply your method in 3D seismic images? And 2, is the employed data set easy to be downloaded?
Yes, the data set is provided by IBM Research, and I think you can download. Maybe you can.
It's publicly available.
Yes, it's publicly available. The name is Netherlands dataset. And it was a geologist from IBM Research that annotated.
Okay.
I don't remember, Danilo, the first question was?
If it was applied to 3D seismic images. Yes.
Yeah, it was 3D, right?
Yeah,
Slices.
yeah,
Yes.
slices of a 3D cube.
Okay. All right. Okay, I think, well, I thank you guys again. Send greetings to Dario. Well, I think we can move to the next work. Thank you very much. Okay, so this work is called Unsupervised Semantic Segmentation of Aerial Images with Applications to UAV Localization. This paper has been accepted in the Geoscience and Remote Sensing Letters special stream of SIBGRAPI. And it was, well, the authors are from the Federal University of Minas Gerais. So let's see the video.
Hi, my name is João Pedro, and I'll present the work Unsupervised Semantic Segmentation of Aerial Images with Application to UAV Localization. This work was produced by Brian Henry, João Pedro Flock, and Christian Leite. In recent years, semantic segmentation of aerial images has attracted a lot of research interest due to its many applications, such as train delimitation, surface change detection, and others. The current state of the art in semantic segmentation is held by the Deep Semantic Segmentation Networks, or DSS, but there are a few problems with these networks. They require a labeled dataset, and they are usually limited to the target domain from the dataset. This could be a problem for some applications, such as UAV localization, where the desired output is not known. Among the approaches to solve the UAV localization problem, a common technique is the template matching, which consists of comparing the UAV image with a source image. Furthermore, the template matching can be improved by the usage of semantic information, such as contextual information of the images. In order to deal with the usage of semantics in the UAV localization problem, we proposed a methodology of semantic segmentation of aerial images, in which the targeted output masks are not known in advance. Therefore, we modeled the problem as an unsupervised learning problem, and provide an application to a template matching-based UAV localization problem. This methodology does not require any prior knowledge on the data and parameter setting, and therefore is suitable for UAV embedded system implementation. We start with the semantic segmentation pipeline. First, we start with an input image from an UAV. Then we apply a smoothing filter capable of preserving the edges of the image. In this work, we use a bilateral filter. We then segment the image into superpixels using the SLEEK algorithm. We define the number of superpixels based on the size of the image. Next, for each superpixel, we extract the mean, extended deviation, aging, energy, and average gradient of both color and texture features. For the color features, we use 7 different color spaces, and for the texture features, we use a Langmuir filter make. These features are normalized both globally and locally, and since the resulting number of features is high, a PCA is also applied to reduce dimensionality. Then we have the semantics with post-processing step. We use the fuzz-semins algorithm to clusterize the features into classes. To define the number of clusters, we use the endpoint of the objective function of the fuzz-semins. Then, in order to ensure the best possible segmentation, we evaluate the fuzz-semins for any x number of times and use the partition with the highest scaling Scalabase index. Finally, we construct a dendrogram with the resulting clusters and make a cut at 1/3 of its height, combining the clusters below. Finally, this will result in the semantic segmentation. An alternate version of this pipeline is also proposed, where we exchange the post-processing step for a classifier. Given that the image has already been segmented, a classifier can be trained using the resulting centroids, and superpixels for the following images can be classified among the centroids of the first image. Before showing the results, we will first show the datasets used in this work. We used 2 datasets. The first is a Brazilian dataset from the region of São Carlos. For this dataset, a georeferenced map is used along with 36 images taken from one UAV. We also manually labeled both the georeferenced map and 10 images of this dataset in 4 different buses. We also used a Sweden dataset from the region of images. Then we explain the semantic segmentation for a UAV localization pipeline. There are a few new blocks in this methodology. First is the transformation step, in which we ensure that both the UAV and map are in the same scale. Then we apply histogram localization both images and apply a histogram matching in the UAV image to ensure that both are in the same space. The global normalization parameters of the map image are also applied to the UAV image. At the end of the UAV pipeline, we also fix rotation of the image with respect to the map and extract only the useful area from the rotated image. Finally, the image goes to the template matching block, where the map is divided into 10 by 10 blocks, and for each block a patch is extracted and segmented, and we calculate the correlation between the edges of the patch and the UAV semantic segmentation. With every correlation calculated, we have a correlation matrix, and then we estimate the normalized Gaussian distribution, from which we make a cut to obtain reduced search area for the UAV. Here we have the results for the position estimation experiments. In this experiment, we compared 3 different methodologies with our proposed approach in a template matching problem, using the georeferenced map for each dataset in the respective images. As the table shows, we obtained better results using our methodology based in the reduced search area in both datasets. In order to ensure good performance of our semantic segmentation methodology, we additionally made a comparison with some state-of-the-art DSSNs, in which we trained each DSSN with 1,000 random patches from the manually annotated map from the present datasets and tested the performance in the 10 additional labeled images from the dataset. Results show that even though our methodology does not surpass the DSSN segmentation, it's close enough to ensure good results in a proposed localization application, with the advantage of not requiring training the targeted application. Finally, we conclude our presentation. In this work, we proposed a novel semantic segmentation methodology that does not rely on deep learning and that is completely unsupervised. That is, it does not require any prior knowledge on the desired output and domain. We additionally proposed improvements in our template matching methodology, where we are able to reduce the overall position estimation error to the usage of our semantics. For future works, we could explore additional uses of the semantic segmentation. We could also provide better estimates for some of the parameters. And finally, we could integrate this methodology with embedded systems. We would like to thank Log, CNPq, and CAPS for supporting this work. Here's my contact information, and the code for this work is public and available at this link. Thank you very much.
Okay. I'll read the question. I would like to thank you, João. And very interesting. So let's go straight for the question here. Is the Brazilian data set used in this work publicly available for download?
Yes, it's available at the link that I provided in the presentation. I think it's under maintenance right now, but it will be available at that link.
Okay. Well, you talked a little fast in the video. It was
there was a lot to talk.
There was a lot of information about it. So interesting aspect of the work is that you do not need ground truth for training. I got confused a little bit about this.
Yeah, the main semantic segmentation methodology is based only in the features extracted, in the color and texture features extracted from the images. So to perform the semantic segmentation, we actually don't need a ground truth. But in the comparison with the DSSNs, we use the ground truth just to compare the images, but it's not required for the semantic segmentation methodology.
Okay. Right, that's
because we clusterize the features. Yeah, we clusterize the features in order to find the classes and the segmentations.
Okay, but then you select number of clusters that is the same as the number of classes.
No, we actually we use the fuzzy Semings algorithm to clusterize the features. So we run the fuzzy Semings for a lot of different number of clusters, and we take the knee point of the objective function curve as the ideal number of clusters.
Oh, okay.
And this will be the number of classes in the final segmented image.
All right. Okay, it's clear now. Yeah, it's interesting methodology. It's semantic segmentation, but you are still working with objects with superpixels per se. So it's interesting that your method competes with deep learning based methods, but do not use deep learning, and still you have good results based on what could be called object-based classification or something like that.
Yeah, our results actually does not surpass the SSNs. as we showed, but we developed this methodology mainly for the application in the UAV localization problem. We developed it thinking about solving that problem. And in that problem, our application is fast and is able to be used in embedded systems. So for that application, our methodology is good enough, even though it does not surpass the state of the art in the semantic segmentation task.
Okay, yeah, but it's you say it's faster. How much faster you be? Can you compare the well, in terms of inference or training?
In terms of training, since it does not require training. In the experiment, we trained it on SVM with the features of the georeferenced map. But this training took under a second, let's say. But in the actual methodology, we do not need any training. So it's faster in this manner, let's say.
Okay. Okay. Well, thank you a lot, João. I don't know if we have any more questions. Okay, from Mateus. Did you try different types of clustering techniques?
In the
you mentioned
beginning of the work, we tried, but yeah, in the beginning of this work, we actually tried other semantics, other clustering methodologies, but this one performed better, and we chose this one mainly because the fuzzy semantics gives a degree of membership of each superpixel to each cluster. And we could actually use this information. We thought about using this information later. If you ever need to know, let's say, if a superpixel belonged more for a class and how much belonged to each class, let's say.
Okay.
So
it's
we thought about using this information.
Okay. It's a mixture of classes inside the superpixel, right? You can try to, I don't know, maybe understand this mixture later. Okay, thank you very much, João. Okay, so now we'll go to the next video. You're welcome. Okay, go to the next work. OpenSet semantic segmentation for multitemporal crop recognition. This work was involved a collaboration between people from the Catholic University of Rio de Janeiro, from USP, and University of São Paulo, and Federal University of Minas Gerais. So let's watch the video.
Good afternoon. This is our project OpenSet semantic segmentation for multi-temporal crop recognition. The motivation is related to the growth in population, which increases the agricultural production and results in ecological impacts. The task of crop recognition is to assign a crop type to parcels in a certain agricultural area. This is a task of semantic segmentation for satellite images in remote sensing. Assign a class label to each pixel from the image. We use the spatial information for this, but also we use the multi-temporal information because each crop type has a particular temporal signature. This is the network that we used in previous work. It is a UNet network with a recurrent network in the bottleneck. But this result, as we can see here, in one of the datasets we used previously, we don't have labeled samples for most of the image. When we make the prediction in the entire satellite image, we see something interesting. This area corresponds to a municipality, Luis Eduardo Magalhães municipality, but we don't have a building class here in our dataset. So the network makes a mistake and cannot classify this region. This is what OpenSet is about. We usually make closed set classification where we assume that all the classes that we are going to see at inference are present during training. But in OpenSet, we want the network to classify regions as unknown. Give the network the possibility to classify as unknown. So our first contribution is to adapt the method OpenPCS or OpenPCA for semantic segmentation to the task of multi-temporal crop recognition. We use our pre-trained unit recurrent network, which input is a sequence of images, and we obtain for each training sample the resulting representation of each decoder stage. Then we do upsampling operation for the smaller representation in the decoder, and then so that they have the same spatial dimensions, and we concatenate channel-wise. Then we fit a PCA for each class in the known classes, and we assume that the resulting low dimension representation follows a Gaussian distribution. We apply a threshold over the log likelihood values to produce the unknown samples. But the OpenPCS has a problem, that the assumed Gaussian distributions are different for each class, yet we use the same threshold for all classes, and this is not optimal. We propose a solution, which is a normalization solution. We call the method OpenPCS++, and we apply a whitening transformation, multiplying the result of OpenPCS times this term, where Sk is the covariance matrix, and resulting in a isotropic Gaussian distribution for each class. Here we can apply the same threshold for all classes. Study areas, we use publicly available datasets in Brazil, such as Campo Verde, where we take a particular date and we select the main classes as known classes and the rest to be classified as unknown. We do the same in another dataset for 2 dates. To evaluate the proposed method, we use threshold independent metric because the determination of a threshold is still an open issue. Here we can see results for the 3 dates, and the proposed OpenPCS++ is better than the baseline. As qualitative results, here we have ground truth, here the closed set classification, so we don't do anything to detect the unknown. The closed set makes a lot of errors, as we can see here, this area. And we can see also that OpenPCS and OpenPCS++ were better, for example, here. Also, there is something interesting that in this case, a closed set prediction classified this area as incorrectly different class, and the open set methods fixed this by saying this area is unknown. We can see here that the predicted image, the municipality is correctly classified as unknown. Also, a no data region is also classified correctly as unknown. As conclusions, the open set approach might help us using the network in an operational environment. The proposed OpenPCS++, it has improved over the baselines, and this work evaluated threshold independent metrics. Thank you. This is our team. This is our GitHub website, and these are the funding agencies.
Okay, thank you very much, Jorge. And Hugo. Okay, we have time for questions. Any questions? No. So you use a multi-temporal series of SAR data, correct?
Yes.
Did you evaluate this using optical data also? No.
No, in this work we only used SAR data. This would be an interesting approach.
Yeah, I understand. It's very important, interesting to work with SAR, but I don't know. It would be interesting also to see some evaluation over optical data, because I mean, probably the results would be even better. Well, certainly the results would be better. Okay. Hugo, I can't hear you. You mute.
Can you hear me now?
Yeah.
Okay, sorry.
Yeah.
We are evaluating also visual data, visual bands of data, and hyperspectral on current works. But in this work specifically, we only use SAR data. Yeah, but we are investigating this line of research also.
Okay. All right. Well, it's an interesting work, certainly very interesting. I would like to talk to you guys to understand it a little better in the future, but I don't know. So, a question from Mateus. What do you think were the main reasons why the whitening normalization improved the results?
Do you want to answer?
Yeah, of course. We had a previous work that was recently published on machine learning, a special issue for remote sensing, about exactly this idea of open-set semantic segmentation. And it only used static images on urban scenarios. And we observed that the thresholding that we need to apply to determine which samples are in and out of distribution varied a lot according to the known samples, the known classes. So the idea of the widening, the idea that the widening improves the results is may result from this disparity in the threshold applied in the known classes. So this was basically the idea that we came up with for this work. That we argue that this is the main factor that results in the best results comparing to the baseline method.
Okay. Well, okay, another question from Mateus. Can you expand further the discussion on the challenges of using multi-temporal data? Well, the challenges and benefits.
Okay, so for the application of crop recognition, we usually have a temporal sequence of data because the agricultural crops, they change over time and they have a particular temporal signature that helps a lot to classify them. So the previous works, they used images. Sometimes it's okay to use images for detecting buildings, vegetation. But in the case of crop recognition, we can only do it with a sequence of images. So this is why we apply the open set to the sequence of images. It doesn't change so much the open set approaches because they are post-processing, and in the end they are very similar to they are analogous to the single image open set approaches. So yes, the contribution we evaluated using temporal sequence, which in a future might be very interesting, for example, to see which new classes are discovered in the future, because it's a temporal sequence, but we don't know how the network is going to behave in the future dates. So maybe in the future days we're going to have new classes. This is something we didn't explore here. We do that. We can do that in the temporal dimension also.
Yeah, very, very interesting. And it's a very hard problem, crop classification, and dealing with this large number of classes. It's very hard. And I mean, I agree with George. It's impossible to discriminate classes using one point in time, only one epoch. I mean, there's a lot of similarities between the spectral similarities. Well, you're using radar data between different classes, and a lot of difference within the classes, because I mean, people can start I don't know, the agricultural process in different times. So I mean, the same crop can look very different in the same image depending on the phenological stage that where that crop is. Okay.
It's also an inherently long-tailed problem. So we have a lot of samples from a few subset of classes and a very small sample set of the majority of classes. So it's kind of inherently out of distribution, an out of distribution problem.
Yeah. Well, since we talked about data augmentation before, did you do any data augmentation during training?
Yes, we used data augmentation as flip and horizontal mirror, vertical mirror during training.
Okay, so the basic data augmentation techniques, nothing very.
Yes, basic.
Okay. Okay. Well, we have to stop here because we have just a little more time for the next video. Thank you, Jorge. Thank you, Hugo, very much, and the other authors of this work. Okay, so the last work is post-text seismic data compression using a generative adversarial network. Okay, the authors are from Federal University of Juiz de Fora and the NVIDIA Research Center. So let's watch the video.
Hi, welcome to our presentation. I'm Kevin Schwantz Ribeiro, Master's student of Computer Science at Universidade Federal Juiz de Fora and the presenter for this talk. Seismic data are mapping from the Earth's subsurface that represents the geological structures present in the region where they were acquired. The improvements in the acquisition methods, especially in the quality of the sensors, have also increased the size of the seismic data. The motivation for compressing seismic data comes from the demand for hundreds of terabytes to transmit and store them. The post-text seismic data are 3D data computational represented as scalar fields with 32 bits precision. The goal of lossy compression is to minimize the trade-off between distortion and bitrate. Hence, the loss of both is balanced. In this work, we use the PSNR as a distortion function, and the bitrate is estimated through a 3D convolutional neural network. The basis of our method was the 3D-based seismic data compression, or 3DSC, proposed by Schiavone. This method is a 3D deep thought encoder that can compress and reconstruct seismic datasets, exploiting the similarity among the neighboring slices. Here we have an overview of this method. A seismic volume is provided as an input and then compressed using an encoder module that generates a latent representation and an importance map. The importance map generates a mask, aims to discretize the latent representation, then the quantization is applied to discretize the elements of this latent representation. This discretized volume is then passed through the decoder in order to reconstruct the input and through the probability model that calculates the joint probability distribution of the quantized latent representation to estimate the associated bitrate. Inspired by the work of Agerson that uses a generative adversarial network, or GAN, to compress and reconstruct natural images, we insert a GAN framework to the 3DSC method. Our method considers the same network used in 3DSC, but with a GAN formulation. In this case, the 3DSC decoder is used as a generator to generate a reconstruction through the quantized latent representation. And the discriminator module is added at the end of the deep thought encoder to discriminate whether a sample is a real input or its reconstruction. Our goal is to improve the 3DSC as a 3D volumetric redundancy estimator. In this slide, we have the reconstruction results for the Poseidon 3D test volume, which is a very noisy dataset. Here we can see an example of its slice and the reconstruction of our method with 0.25 bits per voxel. In this case, the BPG and JPEG 2000 had a better performance compared to the deep learning-based approach. Our method better preserves the lower frequencies but smooths out the very high ones, which explain its lower PSNR for this noisy volume. In this slide, we show a qualitative result comparing a reconstruction 2D slice from Poseidon 3D volume with 0.1 bits per voxel. Our method improves 3D-SC in higher frequencies, although the BPG compressor delivers a higher PSNR. We can observe that BPG blurs several horizons interfaces, and it also introduces artifacts in the right bottom corner. In this sense, 3ds again better maintain the structural details in comparison to the other two methods. Thanks for watching.
Okay. Thank you very much, Kevin.
Thank you.
Very nice work, very impressive results. So it's interesting. It's an interesting idea to work with a gun in the compression. I mean, it's a clever idea. I mean, I didn't have access to the paper before, but so I will, I don't know, ask you again. You said something about it before. What's the importance of this work in the oil business, or what's the relevance of this? Maybe you can, I don't know, talk a little bit about the processes that are involved in analyzing data and transmitting data, or so on.
One example is if you want an application of using seismic data, you would need hundreds of terabytes to store them. So it's not difficult to think about compress them. Imagine 100 terabytes become 3 gigabytes. You know?
Okay.
It's very important to make that available for any storage.
Have you guys thought about maybe using that, I don't know, the latent representation somehow, not only, well, for reconstruction, but for some sort of classification of the data?
Not yet. The latent representation in this work we only use to reconstruct the original data.
No, yeah, I understand. But do you think it's an idea? It's something that can be done?
Yeah, because latent representation it's basically the feature maps of the
It's a
original data.
featurization. Yeah, it's a featurization of the input. Yeah, that's an idea. Okay, so Hugo, did you observe any artifacts from the naturally unstable adversarial training of guns? Wouldn't a non-adversarial, more stable strategy be more promising for comparison, for compression? Sorry.
That's a good question. We use PSNR as a loss function and rate distortion function. So it uses MSI to calculate the difference between the input and output. So the PSNR it's basically shows the noise between the noise inserted in the original data. But as I showed in the video, our method has better reconstruction results compared to the BPG, and also these artifacts is more present in the BPG method.
Well, are you still there, Kevin?
Yes.
Okay. Tell me a little bit about the effort in training, the training process.
We select three data sets and extract slices from them of dimensions 160, 160, and the deep size. The deep size we vary during the training, and the paper shows the tables and our results. In the video, I showed only the approach with 12 slices,
Mm-hmm.
and the training is applied with them. Then we validate it with only one noise dataset. To then we we test with the others 5 datasets. These
Okay.
5 datasets are composed by this noise dataset Poseidon that is hard to compress, but the others it has medium and easy difficult compression.
Okay. Okay. So thank you again, Kevin. Thank you very much. We are approaching the end of the session. We have exactly 1 hour and 2 minutes. So, well, you can continue the conversation at this Discord channel if you want to talk a little more with the authors of the works that were presented here. And well, please stay tuned for the next SIBGRAPI session, tutorial 4, and the workshop of the industry application. I don't think we have a plenary in a few minutes. We don't have no session after this one, but then there is this workshop tomorrow morning of industry applications. Well, thank you all very much for being present here in this session. And well, with this, I close the session. Okay, goodbye. Goodbye, everybody.